Okay. Hi, everyone. Welcome to CNTC seminar. Our speaker today is Cory Dean from Columbia University. Cory is a renowned experimentalist in two-dimensional material, including graphene and transition metal dichalcogenide systems. Cory did his PhD in McGill University, then a postdoc in Columbia. Now he's faculty in Columbia University. He's going to tell us about his recent exciting results on the correlated phases of twisted TND systems. Cory, please take it away.
Okay, thanks, gang. Just let me know when I've got about 5 minutes left. I think I'll finish in time, but if I'm going to go long, I'm happy to stop whenever the time's up. So just let me know.
Actually, we don't have a time limit, so.
We
don't force those things. You know, we only invite people whose work we are interested in. So
okay.
You should not go on for 2 hours, but if you do, I will still be here. Okay, so
okay, fair enough.
So don't worry about that. Okay, don't rush. Tell us everything you want to say.
Okay, the other thing is, especially in the era of Zoom, you guys have been doing this for a while, so I'm sure you're familiar with this, but please just stop me at any point and ask questions. If somebody wants to text a question, I'm not going to monitor the text, but if somebody else can just read them to me, that's fine. The other thing I just want to say is up front, so I apologize, I sent a different abstract than what I'm going to be talking about in detail, but in generalities, it's kind of, there's some overlap, as I'll explain in a minute. Okay, so thanks for inviting me to this virtual seminar. It's my pleasure to describe some of this work with you. Originally, I was going to talk about some quantum Hall bilayer stuff, specifically about exciton condensates in graphene double layers. But in sort of talking to Sankar and others recently, I realized that you might be interested in hearing a bit more detail about our work on transition metal dichalcogenides. So I'm rather going to focus on that today. And again, stop me at any point if there's questions. Okay, so first to just motivate very simply, what are we talking about today? Even though the material platform is going to be transition metal dichalcogenides, in essence, what we're talking about is what happens when you have a flat band in a system. So this very simple cartoon picture, which everybody here is familiar with, of a kind of band theory of electrons in a material, describes how you fill electrons in material according to the Pauli exclusion principle, et cetera. Okay, so the critical points here are that we have a Fermi energy we can well define, et cetera. Now, what's going to be interesting today is to think about systems that don't look like this conventional band structure, but instead have some kind of low energy flat band, as it's called. And what are the characteristics of this flat band? So one is that the energy width of the band is much less than the Coulomb energy in the system. This means that unlike in conventional kind of single particle theory, in this case, kinetic energy is suppressed or at least smaller than the Coulomb energy, which means Coulomb energy now dominates. And historically, whenever you can create a scenario in which Coulomb energy dominates and the electron properties are determined by how the electrons interact with each other, generally interesting and often spectacular sort of physics results. So this is a longstanding challenge in physics community in general, how to realize such a system. The other thing that may or may not be relevant is that this low energy band that we're considering is reasonably isolated from any other kind of dispersing band in the system. Okay, so one just kind of point I want to make, which is that I've been studying in my own career flat band systems for more than a decade. So there's really a lot of interest in twisted bilayer graphene recently. But before that, before the decade ago when I started, many decades before that, people realized that there's a really nice way to realize flat bands, which is to take a conventional two-dimensional material and apply a magnetic field. And when you do that, this dispersing band breaks up into what we call Landau levels. And the relevance here for this talk near the very end is that these Landau levels are also flat bands. They're characterized by the fact that you have a suppressed kinetic energy and Coulomb energy can dominate. And as a consequence, interaction between states can appear. So in a sense, any physics that we explore in the quantum Hall regime, in my view, has direct sort of, relevance and can provide insight into what happens with regards to these flat band systems at zero field, although there are some differences in specific details. Okay, so what I'll be talking about today is almost entirely the first version of a flat band system I described. So we're going to talk about correlated states and Moiré flat bands. So these are flat bands that arise as a consequence of realizing some kind of Moiré pattern in the system. And we're going to be looking at twisted bilayer heterostructures mainly. So as I mentioned, everybody almost certainly by now is familiar with graphene. Graphene famously was shown by Pablo and MIT 2 years ago now. If you took two graphene layers and twisted them to the so-called magic angle, then at that magic angle, you can realize a flat and isolated low energy band in the system. And in that system, correlated states emerge. So what he showed initially was that you get a Mott gap, a half filling of that low energy band, and you also get superconductivity when you dope outside of the Mott gap. Okay, so it's important to, or maybe relevant to understand, where does this flat band actually come from, or what's a picture we can develop in our minds of where it comes from? I think I showed this picture to, in a talk I gave in Maryland about 1.5 years ago, but it's relevant because I want to draw distinctions between what we're going to be talking about in TMDs in a moment. So in graphene, bilayer graphene, imagine I have a lattice and I put on top of that a second lattice, and what I'm showing here below is just the linear dispersing energy band. As I twist these lattices, one relative to the other in real space, what happens is in K space, these two bands centered at the K point displace. And after they displace, what can happen is these bands can hybridize. And what that does is it opens up a band gap at some finite energy. The width of that band gap is related to how strongly interacting the layers are. And as a consequence of opening that that energy gap at finite energy, in a sense, you're kind of left with this low energy band. And this low energy band has a definite width. Now, what happens is as you rotate one lattice relative to the other, the point in energy space, in energy momentum space where this band crosses, shifts up and down. So if I rotate these lattices, then I can shift the point where that hybridization gap emerges. And as a consequence, eventually, I end up varying the ultimate width of this flat band. So as I rotate back and forth, I can tune this bandwidth up and down. Now, what happens is if I tune, to too small an angle, I kind of push through the point where I have a definite, flat band, and I lose that flat band again. So there's a precise kind of condition that you can, in a hand waving cartoon picture, identify you want to realize, which is that I want the width of this band to match, or the half width of this band, to match the distance from this crossing point to the intrinsic crossing point. And when I reach precisely that condition shown here, then I have a minimally flat band. So that can be sort of drawn also in sort of a quasi-schematic way here. As a function of twist angle, in blue here is basically the size of the bandwidth. Red is the Coulomb energy in the system as a function of twist angle. Here, the Coulomb energy varies as a consequence of the site-to-site distance between the Moiré unit cells. And essentially what is found is that there's a precise angle or narrow range of angles over which the bandwidth becomes smaller than the Coulomb energy. So what that means is there's a defined range of angles over which we might expect the system to host correlated physics because the Coulomb energy dominates. Okay, so this is the so-called magic angle. Now what's relevant here, I think I forgot to put the full band structure, but what's relevant here is, as was identified by the MIT group in their first paper, this band becomes extremely narrow at the magic angle. Sorry, that was identified previously by two or three theoretical papers, including Alan McDonald, et cetera. So the point is that this band becomes extremely narrow at the magic angle. And the other point is that the bandwidth varies rather rapidly with twist angle. So it's really only within about 1/10 of a degree around approximately 1.1 degrees where you expect to be in the so-called flat band condition. Okay, so since the discovery by Pablo...
Cory,
yep,
Cory, may I ask a historical question that really has bothered me? So
Sure.
You explained the flat band arising extremely well here. And it's a very simple idea. And this idea has been around for a while. There is Alan McDonald's paper, but people talked about creating flat band from graphene even before that. The concept of magic angle wasn't there, but the fact that the band would flatten because this is such an elegant picture. And, people have written papers. I have written papers that if you have flat band, great things are going to happen. In regular 2D system, people are going to very, very low density, trying to make the mass very heavy to see the same physics. But all that physics is here beautifully.
Yes.
Why didn't it happen before? I mean, what was holding it up? This is just an amazing system, and the system just looks like what theorists would like it. But why did it happen in like 2018 and not before? What's the reason?
That's a good question. Part of it was just sort of getting around to it. So I think, historically, indeed, these ideas were around for a long time, even going back to STM data before it was all kind of fleshed out, identifying that there are Moiré patterns and band structures, et cetera. So I think my own view is that it was a challenge of, there was just a technical concern about how to realize the system. So, when I was traveling around probably 5 or 6 years ago, I would routinely encounter, have conversations with visiting, hosts at institutions I would be talking at, who would, like theorists, who would point out, if you could realize this physics, you would see something spectacular. They would often say, if you can realize this kind of like twisted layer system, then it's going to do this. And this was always like something extreme. Superconductivity, frustrated magnetism, spin liquid.
Right, yeah.
So why don't you do that? And we thought seriously about it. So I think, I've told this before, in my own group, I was working with Matt Yankowitz, who prior to that, had done STM work. And what we intimately knew was that there's a significant disorder problem in the system. So I'm not going to talk a lot about that today, but what we knew, because we saw this by, STM, knew as a community, because we saw this by STM imaging, is that if you try to make a device at a fixed twist angle, it's very angle disordered. So as you go from one location to another, the twist angle varies rapidly, et cetera. So we in my group had a conversation, should we try to do this? And our agreement was, even if we could get something close to this angle, it would be so disordered that there would be no hope we would see anything coherent. And so we weren't substantially motivated to pursue that at that time because of that. So I think that was, but then a series of things happened. One of the critical things that happened was the Tutu group in UT Austin developed a technique that would allow you to make a twisted bilayer device at an angle that was determined pretty well without having to know a priori what the lattice orientation was. So that made the idea of pursuing this much more accessible. And then, then it went from there. Okay. I don't know. Is there more to that question?
Yeah, I think you have explained the main thing. The disorder issue was crucial. Materials development took place, and how to fix the angle got figured out more or less all at the same time. So things happened. Right. Okay. All right.
Yeah. So I wanted to just a little bit respond to your point. So we thought the angle disorder would be crucial, and in the end result, one of the more surprising things to me is that coherence does develop in the system, in spite of what we know in terms of there being a large variation in local Moire wavelength, for example. So that's kind of, to me, there's sort of this tension that hasn't been totally resolved, which is that the band structure varies dramatically with twist angle. So you would think if there's a lot of variation in twist angle, then you would totally obliterate any hope of having some kind of coherence in the system. And yet we know that disorder is present in that way, and still coherence develops. So there's, that might be something that may be trivial in the sense of like when we're talking about coherence, we're talking about superconductivity. And if there's any superconducting path through the system, then you'll see it. So maybe that's just, means that there's sort of a robustness against disorder, or maybe something to think more detail about is sort of what role strain is actually playing in the system and how to understand that in detail, et cetera.
Yeah, I think the twist angle disorder question is still open. And I looked at it with Jeff Pixley in some depth. And I agree with you that why that disorder is not manifesting itself much more prominent in experiments is an open question. Yeah.
Yeah, and maybe it is, and we just don't realize it. So this might be questions about, for example, critical temperatures that are realized, or critical fields, or things like this. But
okay,
okay, good. So this, I realized I didn't update these are all archive listings of papers that are now published, and this is just kind of the first slew identifying some of the early work identifying properties of the system. There's many more now, and I didn't sort of list them all. But what I wanted to highlight, as Sankar just pointed out, is that the remarkable feature of this system is that, as far as we can tell so far, if there's any sort of interesting phase that you would want to look for in a material platform, it's present in this platform. And that's a remarkable fact that's emerging. So what's been observed is superconductivity, Mott insulator, ferromagnetism, churn insulators with different churn numbers. Recently, pneumatic ordering has been identified, et cetera. And not only are these different sort of phases present in this platform, they're highly tunable, and they're tunable in relatively trivial ways. So one way to tune in and out of different phases that I list here is through varying the twist angle maybe a little bit, or in a more facile way, just electrostatic gating can sort of dope you to a regime where you have one phase or another. So that really is like a remarkable, in my view, a rather remarkable sort of evolution in terms of how you might think about materials engineering even, and what we might do with this material platform in terms of integrating all these different properties together going forward. Okay, so one thing that I just pointed out is that there's a lot of disorder present in these systems. What that means is that while we see a lot of qualitative similarities between devices. Details are often different, so I'm just pointing out one example here. Here's an example where, for example, at some doping in the conduction band of the system, there's a superconducting pocket that exists in this particular device. There's not in this device, which nominally is around a very similar angle. This is a different group publishing between these two. This is our data, and I think this is, I think Dmitry Eftov's data. They see superconducting pockets where we see none in devices that nominally are the same. There's a question about whether disorder is playing a role here in terms of suppressing or enhancing these pockets or not. And there's just a lot of questions that are not resolved. And the reason for that from an experimental point of view is that the system just varies so rapidly with small variations in its physical structure that it's difficult to get a handle on from device to device, what really is changing, what's important and what's not important, et cetera. So that being said, I just want to emphasize that, broadly, there are broad trends. So here's two plots that came out in papers in the past year showing some statistics of how the critical temperature associated with the superconductor varies as a function of angle measured across devices. And what you see is that, while there are exceptions to the trend here, sorry, I lost my pointer. Here, for example, these green dots are sort of outliers in the background. Roughly what is the case is in terms of superconductivity anyways, the superconductivity tends to peak, its critical temperature tends to peak very close to the magic angle and sort of falls off away from that. So this suggests that although details from device to device are can be very different, broadly the average sort of, understanding of the theoretical nature of the system, our average theoretical understanding of the system kind of broadly matches average experiment in some way. Okay, so there's a lot more to do in terms of understanding twisted bilayer graphene and manipulating it and doing cool new things with it. What I'm going to ask today is, what about other 2D materials? So as we know, there are many materials that can be exfoliated to the monolayer limit. And if we can exfoliate any of them to the monolayer limit, then in principle, we can stack one on top of another and play the same game of twisting, for example, or lattice mismatching. And in those two ways, finding some way to induce a Moiré superlattice potential and look at how that Moiré superlattice potential modifies the band structure of the underlying crystal. And in particular, what we're interested in is, can we induce flat bands and correlated states in a similar kind of way? Okay, so what I'm going to focus on today is a subset of these exfoliatable materials. These are called the semiconducting transition metal dichalcogenides. These are all characterized by having approximately similar structure, which is some kind of transition metal bonded to two chalcogens, forming that three kind of body system forming a monolayer structure. So let me show what that crystal looks like. So here's a top-down view of the material I'm going to talk about mostly today, tungsten diselenide. And here's the edge-on view. And as I said, there's basically a layer here of transition metal ions, the tungsten, bonded up and down to selenium in this case. And if you look top down, this has a honeycomb structure, just like very similar to graphene. And the band structure also is very similar to graphene. So here's a picture of the band structure here. What we see is that just like graphene, we have cones at the K and minus K points in the Brillouin zone. Unlike graphene, what we notice is that these systems are gapped. They're semiconductors. And so although these, dispersing cones somewhat resemble what you see in graphene, they're often characterized or described more as like massive Dirac cones. They have an approximately linear dispersion away from the bottom of the band, but they're approximately parabolic near the bottom of the band. Okay, so here's what a kind of real band structure calculation looks like in such a system. What you see, or what's relevant to understand, that's unique about the system in comparison to graphene. First of all, there's a band gap. Secondly, there's a strong spin orbit coupling term that's present. And the consequence of that is to actually partially lift the valley and spin degeneracy in the system. So graphene has spin and valley, so fourfold degeneracy. In these systems, what happens is, if I look at one of the K points, the spin up and spin down split as a consequence of spin orbit coupling. And if you look at K prime, the same thing happens. But what we notice is there's kind of what's called a spin valley locking. So I end up with one band being mostly spin up and the other band being spin down. So whereas if I didn't have spin orbit coupling, I would have a fourfold degeneracy. I'm left with a twofold degeneracy, and we can characterize that twofold degeneracy as kind of a combined spin and valley pseudo spin. So one band now has K up and one K spin up, one has K prime spin down. Okay, so for the rest of this talk, what I'm when I talk about band structure in the system, I'm going to almost exclusively be talking about this part of the band structure here. So I'm going to be thinking about working in the valence band because experimentally, when we make these materials, we tend to be nearly doped to the valence band, so we can tune into and out of the valence band easily. And the other thing I'm going to do is for this talk, I'm going to ignore basically this lower spin split band. It's not going to be super relevant for what I'm talking about. So going forward, imagine that the system I'm thinking about is that I have one band at the K point, which is spin up, and an equivalent degenerate band at the K prime point that's spin down. Okay, so theoretically, people have looked into the question of what happens if I stack homobilayers of semiconducting exfoliatable materials and twist them. And the short answer is that you get flat bands, and those flat bands seem to be ubiquitous. So BN here is not necessarily a transition metal dichalcogenide, but it's also a 2D insulator. So the short story is that flat bands emerge, they're everywhere, and there should be a lot of sort of fun we can have looking at flat bands in these systems, similar to what we see in graphene, but with the addition of new properties, for example, presence of spin-orbit coupling. Now, it's important to note that the flat bands in these systems arise, to my mind, from a different cartoon understanding of what I described for graphene, and that difference is actually important to understand. So I'm going to go through that a little bit. So just to remind you, in twisted bilayer graphene, we have these linear bands that are shifted in K space. I get a hybridization between the bands, and I'm left with a low energy isolated band whose flatness depends on the twist angle. Which is maximally flat at a very definite twist angle, 1.1 degrees. For the transition metal dichalcogenides, I can invoke the same picture. I can imagine that I have one layer on top of another and I twist them. And now what happens is I have a gapped massive Dirac band in one layer and a massive Dirac band in the other layer, and they overlap a little bit. And the same thing can in principle happen. Where these two bands cross, the bands can hybridize. And then I'm left again with like a low energy band and a high energy dispersing band, but fundamentally different from twisted bilayer graphene. In this case, let's focus on the valence band. In this case, the top of the valence band is fixed by the intrinsic gap of the system. There's kind of a hard limit there. So now what happens is this low energy band, its total width is determined entirely by the position of this crossing point and the width of this hybridization gap. So just like in twisted bilayer graphene, as I twist these two materials, these two cones will move further apart or closer together, and the crossing point here will shift up and down. And as a consequence, I'll vary the band width. But in this case, the bandwidth becomes maximally narrow when I go to a very small angle. So another way to think about this is that in this system, there isn't really a definite magic angle. It's rather that there's a continuum of twist angles over which the band continuously varies. And experimentally, that's quite relevant, because what that means is that unlike in twisted bilayer graphene, where I have to be at 1.1 degrees plus or minus 0.1 degrees, in this case, there's a much broader range of angles that I can tune the system to, and hope to be in a condition where the Coulomb energy exceeds the bandwidth. So the way we kind of glibly summarized this in the past is that rather than a magic angle, I have something more like a magic continuum. So all the way from 0 degrees up to some large twist angle, large being a few degrees, 5 or 6 degrees, we think that we can be in this condition where Coulomb energy dominates over the kinetic energy of the system. Okay. So let's explore that physics in a real system. So what I'm going to be, again, looking at specifically is tungsten diselenide on tungsten diselenide, a homobilayer. We're going to twist these two layers to some finite angle. Here's just a recap of the band structure that we imagine we would have. We've got the intrinsic gap, what I'm calling a Moiré gap, which separates this kind of low energy band at the top of the valence band from the dispersing part. And we're just going to call this a flat band. Okay, so here's a measurement of such a system. What I'm doing is transport measurements. So we do a 4-terminal Hall-bar geometry. And here I'm plotting the resistance as a measure of density in the system. So in blue, I'm showing the response for a device that's twisted to 4.2 degrees. And in black, what I'm showing is, just for comparison, a naturally occurring Bernal bilayer WSC2. Now, just for those who are a little bit more maybe experts in this area, we would consider Bernal 60-degree rotated away from how we're making devices. So we make devices, we take a single sheet and we cut it in half and place it on top of itself. If you wanted to get to the Bernal condition, you'd have to twist that all the way to 60 degrees to be in the more kind of naturally occurring stacking configuration. Okay, so in Bernal 60-degree orientation, what I see is as I dope into the valence band, there is just a resistance that continually decreases as I dope more and more. For the cases of 4.2-degree twisted device, what I see are two rather unusual and dramatic features in terms of transport response. There's a weak peak that occurs at some large-ish doping, and there's a stronger peak that occurs at a smaller doping. Now, what I can show is if I look at this response as a function of temperature, then I'm going to focus on this feature that we're going to call half filling. I imagine that this feature that we call half filling is occurring when I half fill this band. So I take this isolated band and I put my Fermi energy, my chemical potential at exactly the halfway point in this band. And what we find is that this resistive feature really is activated in the low temperature limit, and it disappears abruptly at some finite temperature. So this has all the hallmarks, at least in transport, of what you might expect for a Mott gap emerging at half filling of a reasonably flat band. As I dope away from this half filling, then the system is very much metallic, all the way down to the lowest temperature that we can measure. So the other thing I can do is look at this feature in slightly, this kind of range of density in slightly more detail in magnetic field. And I'll talk about this more in a minute, but for now, the things to point out that we can identify is that, so here's B field on the vertical axis and just density on the horizontal axis. So here is just real density units. Here I'm re-plotting the density units in terms of normalized to what we call full filling. So here, N over NS would be full filling would be 1, would be I completely fill this band. N over NS equals half means I half fill this band. And what we can do is we can identify Landau fans projecting from the intrinsic band edge. Remember, this is the valence band. So negative value is moving the chemical potential down in this valence band. So in near the top of the valence band, the Landau fan that I can identify, I can project this Landau fan to a point at 0 field. And that actually gives me a really nice measure of where the absolute top of the valence band is in our gating scheme. I also identify a second fan that emerges that projects to another point, and that projects to a point that we can identify as the other edge of this low energy band. The other thing to note is that I noticed that the Landau fan that points to the top of the band is twofold degenerate, which is what we expect for the twofold degeneracy that exists in our system. Once I kind of find where these fans project to in gate voltage, I can use those values to convert to filling, and that's how we make this map here. And what we can confirm is that this resistive feature really exists precisely at half filling within the resolution that we can identify. The other thing we note is that the sign of the Hall resistance inflects as we go through the band. So it starts off with a hole-like response, and then it changes to an electron-like response as we tune to the other edge of the band. And that we would expect for the case where we have kind of a closed band. And again, I'll talk about that more in a moment. Okay, so
now,
go ahead.
Cory, I have a question.
Yeah.
So the feature that this full filling and half filling, I noticed something interesting that I didn't notice before. Here, the half filling, the Mott insulator, is a much stronger insulator than the band insulator at full filling,
Yes.
which is different from twisted bilayer graphene, right?
Yes.
They are the most important insulator is the trivial band insulator. Here, it seems to be not the case. Do you have any comment on that?
Yeah, so when we did, when our collaborators did sort of the band structure calculations for the system, this cartoon picture that I'm drawing is misleading. What we find is that actually there isn't a strong gap that isolates this low energy band from the dispersing band. They actually weakly overlap.
Oh.
By band theory, they weakly overlap by band structure calculations. And so that's consistent with what we find. And in fact, I don't think I'm going to show this, but in fact, this resistive feature that we measure is seen in transport. It's not actually seen in capacitance. And so we think this resistive feature is not even exactly a measure of the presence of a gap. It's a measure of a local low density of states in the system.
Okay, I get it.
Yeah.
Okay, it's a band overlap. All right, thanks.
Yeah, good, yeah. Great question, thanks, yeah. Okay, so we think that we identify these features correctly. So now what we can do is we can vary the twist angle and see what happens. Oh, sorry. So as we vary the twist angle, so the device we were just looking at was 4.2 degrees here. we can go to larger and larger twist angle. And what we see is that we continue to see a feature at half filling, but that pushes to higher and higher density. This is consistent with what we would expect in terms of the density units because the bandwidth is changing. We can sort of explore from a maximal angle range of a little bit larger than this, almost 6 degrees. And then if we go to too much smaller twist angle, we run into a technical problem where basically the features of interest that we might want to understand, for example, the half-filling Mott gap, starts to get pulled into the disorder limit, which is sort of a region around the very top of the kind of unreconstructed valence band, where in that low density limit, it's very difficult for us to make good contact with the system, and the electron mobility, or hole mobility in this case, becomes quite low. So it's hard for us to resolve things in transport features. So that's just to say that, you know, even a little bit beyond what's shown here, the entire range that we can experimentally access in the system so far by transport is about a 3-degree twist angle to about a 6-degree twist angle.
So am I understanding you right? You are saying the shaded region may not be an intrinsic disorder induced mobility edge. It could be a contact problem. Is that what you just said?
Yeah, it's sort of both. So if we look at these systems by capacitance spectroscopy, we can substantially push further how down in this band we can measure compressible response. So I think this is, I don't know exactly how to relate those two observations, but it's you know, at least in transport we can't access this region in density, whereas in capacitance we can go much closer to the band edge. I don't know if that helps. I don't know if that really addresses your question.
Yeah, we should talk about it, because, you know, if you already also have disorder interplay here, then all aspects of condensed matter physics are fulfilled, you know, interaction, disorder, band structure.
Yeah, that's right. That's right. Yeah.
So I would not want it to be a contact problem, but let's talk about it later.
Yeah, okay. Good, yeah. That's a good point. Okay, so there's some ways we can address that even in capacitance, but we'll talk about that, yeah, later. Okay, so what we've done is we vary the twist angle, and we see that in, without getting too much into the details, that what we expect as a function of twist angle is the bandwidth varies. And what we see is that that's indeed true. So here, remember, this is real density units. So the density position at which the half-filling peak appears shifts systematically the twist angle, which is exactly consistent with what we would expect. Okay, we also see that there's some variation in the strength of how resistive this feature is, and I'll come back to that later. The next thing we can do is we can look at, because this is a bilayer system, we can look at the consequences of applying an out-of-plane displacement field, so an electric field across the two layers. And what we see is that that has a pretty dramatic effect. So here's a map of, sorry, I forgot to point this out. So not shown in this picture, there's a gate in our devices on the very top, and there's also a gate on the very top, bottom. So what we can do is we can independently apply a bias to the top and bottom gate. And as a consequence of that, we can vary independently the density of carriers in the system separately from the electric field that we apply across the two layers. So in this plot here, what I'm showing is resistivity measured as a function of top gate bias and bottom gate bias. And this dashed line here corresponds to, for this particular twist angle, 4.2 degrees, it corresponds to the density at which we expect to be at half filling of the low energy band. Excuse me. And if I go in this direction in this map, that's varying density. If I go in this direction in this map, that's varying displacement field. So what we see is that at this fixed half filling density position, as I vary the displacement field, there's a quite tightly kind of focused regime of displacement field where the resistive feature at half filling is large, and away from that in both directions. So if I go to small displacement field or high displacement field, that resistive feature basically goes away. Okay, so the next few moments, I want to kind of try to understand that result. So how do we understand that? So the first thing is to just sort of map out what I just said. So here's just 3 line cuts taken along this line, along this direction, varying density, for different displacement field values. So it's at a point indicated here by the green, the yellow, and the red marker. And what we see is just reflecting what I just stated in words. As we vary the displacement field, the height of this resistive feature at half filling changes, and it changes non-monotonically. We can do activation measurements and extract gap values as a function of displacement field. And what we see is that really there's a narrow range of displacement field where the system looks like it's insulating behavior, first of all. That changes to metallic on either side. And we can extract the value of the gap associated with the insulator and see that that follows an evolution as we vary the displacement field. So really there's like a reasonably well displacement field value where this Mott gap value is maximized. Okay, so what's the origin of displacement field dependence? So the one clue to that comes from going back and looking at the Hall response. So this again is just the plot on the previous slide. Rather than focusing on the longitudinal Hall response, I want to focus a little bit, the longitudinal magnetoresistance, I want to focus on the Hall resistance. And as I said previously, what happens is we see that the sign of the Hall resistance inflects as we move through this low energy band. Let me take, for example, a similar plot, but measured from a different displacement field value. So this is measured at a displacement field value of 0.25 volts per nanometer. That's indicated by this dot right here, where this peak is well defined. Let me take another area where this peak is missing, where I no longer have a Mott gap at a larger displacement field, and look again at the Hall resistance. And there's a few notable differences between these two results. So in the first case, what I see is that actually, if you look in detail, the sign of the Hall resistance changes 3 times. It goes from hole to electron to hole to electron, et cetera. Whereas in the case for the larger displacement field value, that's not true. Here, the Hall resistance inflects only once. The other thing that's important to note is that here, at least one of those changes happens around half filling, whereas in this case, there's no relationship between where the Hall changes and half filling of the band. So this result we can actually understand from a very simple kind of band picture. So here I'm drawing the top of the low energy band. I'm imagining it's a closed band, and for the moment I'm thinking that there's no Mott gap in the system. I just have a low energy band that I'm basically just cutting off the top of the valence band. And what I would imagine is that in the system there has to be a point where the curvature of the band inflects, and that's what we might normally identify as the Van Hoff singularity. And for a doping above that point, I would expect a hole-like behavior, and necessarily for doping below that point, I would expect an electron-like response. Now, if I took this band and I introduced a subband gap, so for example, a Mott gap appears in the band, then in this case, I would expect that I introduce a necessarily additional inflection points in the curvature of the band. So now in this case, a simple argument suggests that I should get 3 inflection points. So again, I should transition now from like hole-like to electron-like, back to hole-like as I pass through the gap, back to electron-like, et cetera. Okay, so the 2 results that I just argued, that I just showed, I'm arguing can be explained by these 2 different pictures. In one case, I have a subband gap. In the other case, I don't have a subband gap. So I can look at that in a little bit more detail. Here's just line cuts of the Hall resistance at 3 different values of the displacement field value corresponding to these 3 different line cuts here. And indeed, in this case, I'm at a very low displacement field value where there's no strong insulators seen in the longitudinal resistance, and I see a single inflection point in the Hall resistance. Then if I go to a displacement field regime where there's a strong gap at half filling, I see that this Hall resistance changes 3 times. And then here I'm just showing at a larger displacement field value where again, I get multiple changes of the Hall resistance. But in this case, the position of the inflection points is varying quite substantially from where it was in the first case. Okay, so what I can do is I can actually focus on this feature here, and I can track how this feature evolves as a function of the displacement field. And what I can see is that it continually pushes out to further and further doping away from the half filling point. And here in black, I'm just plotting that feature. So I'm plotting the identity of this inflection point that we're calling the Van Hoff singularity as a function of displacement field. And what I see is that it starts off actually slightly below half filling at very low displacement field. And then the position of this feature pushes through half filling as I increase the displacement field. The other thing I note is that here in red, I'm plotting the peak value of the resistance at half filling. And I see that the resistance at half filling is maximal when the Van Hoff singularity position is nearest to half filling. Okay, so hopefully that makes sense. I'll summarize that in a moment. Before that, what I want to point out is that our collaborators who did band structure calculations for us found that there's a good correspondence between what we see here experimentally and what you might see theoretically if you take this twisted bilayer system and apply a transverse displacement field. And the basic picture is this. So this is now the detailed band structure calculation. So Sankar, to your question, this blue and dashed line is basically the very top of the valence band. This is the low energy band. This is now the dispersing band. And what you see is that these actually overlap. Even in theoretical calculation, it's not a truly gapped system. The coloring here is that the solid line corresponds to the band coming from one of the layers, and the dashed corresponds to the band coming from the other layer. So just like here and here. But now they're hybridized. So there is this sort of, gap between the two. Okay, so this is at zero displacement field. As I apply a displacement field, what happens is I shift the energy position of the unhybridized bands in the two layers. But of course, they continue to hybridize. And as a consequence, I distort this low energy band. This is the basic picture. So that's shown here and here. Now, when I distort this low energy band, two things happen. One is that the overall width of the band actually changes as a function of displacement field. And the other thing happens is that the Van Hoff singularity that you identify in the band, its position actually shifts in momentum space. Okay, so I can summarize those two results here. So here's just density of states calculated in this low energy band as a function of displacement field. And here what I'm identifying is the Van Hoff singularity position, the density value position of the Van Hoff singularity in this low energy band as a function of displacement field. And what we see is that at zero displacement field, the Van Hoff singularity in the band, so this is single particle band structures, so I'm assuming that there's no many body gap that opens. The Van Hoff singularity position actually exists slightly below half filling at zero displacement field, and it pushes through half filling to some higher value as we apply a displacement field. So that actually shows remarkable correspondence with our experimental data, which gives us, we think, confidence that we've interpreted this feature correctly, and also gives a clue to what's going on in the system as we apply a displacement field. Okay, so that was like a little bit complicated. Is there questions about that? Is that followed, or I can just move on? Okay, so if no questions, then I'll move on. So we can do all of that analysis, all of this analysis I just went through, we can do for different twist angle devices. So here on the left is a 4-degree device all the way to 5 degrees. And here I'm plotting displacement field on this axis and basically doping around half filling in this axis. And what we see is that in all of these devices, there's a range of displacement field over which we see a resistive peak or an insulating state emerge. We notice that that insulating state always emerges at half filling, and it shows a finite range of displacement field. But the range of displacement field over which that half filling peak spans varies as a function of twist angle. So 5 degrees, it spans a much larger range of D, for example, than at low twist angle. At even lower twist angle, it's the case that it seems to be the case that we would only see this half filling Mott gap at basically near zero displacement field, and any displacement field would probably kill that gap. Okay, so here's a summary of kind of the experimental data again. So here in the left, all I'm plotting is basically for select twist angles, how the size of the gap at half filling varies as a function of D. And what you see is that, as I just said, the range of D over which the gap exists is bounded. But also the magnitude is sort of different for the different twist angles. What we see is that the largest gap at half filling actually appears in the 5.1 degree device. Okay, so here is just a cartoon summary of our data. We're mapping here, basically going back through these data plots, identifying where the material device is insulating in a metallic from the temperature dependence, and just mapping an overview of, as a function of twist angle and displacement field, this is at precisely half filling. When is the half filling state insulating? That's in the pink region. And when is it metallic here and here? And here what we're doing is comparing that to just integrating the band structure that was calculated theoretically and plotting against where we think, against the density of states as a function of angle and displacement field. And what we see is that broadly, there's a good correspondence between our data and the magnitude of the density of states at half filling that we would calculate theoretically. Or another way to say that is that the insulating feature seems to be present when the density of states is maximal. Or another way to say that is when the Van Hoff singularity, which moves as a function of displacement field, when it's coincident with half filling, that's when we see a Mott gap. And when it moves away from half filling, that's when that gap diminishes. Okay, so just to summarize that, our correlated gap always appears at half filling. But as we shift the position of the Van Hoff singularity in our interpretation, the Mott gap stays at half filling, but its strength depends on how close to the half filling point the Van Hoff singularity is, or how large the density of states is at half filling. Okay, so I just want to kind of emphasize that the understanding that I just sort of described for the system is substantially more clear than was and kind of remains to be the case in graphene. One of the reasons is in twisted bilayer graphene. One of the reasons is that we think that we can identify well the position of the Van Hoff singularity in the system. And the other is that we think we understand how the Van Hoff singularity is shifting as a function of displacement field. And in the early days of matching out graphene, this was sort of a theoretical question that kept coming up. When superconductivity is found in the system, for example, is it coincident with the Van Hoff singularity or is it not? And that's still not exactly understood, I don't think. I mean, there's some conjecture, but I don't think there's been definitive experimental measurement that says, yes, we know where the Van Hoff singularity is in that system in a similar way as we can identify in this system. Anyways, this is a consequence of the system being a little bit simpler to deal with overall because of where the flat band comes from in the system. Okay, so
question.
Yeah, go ahead. Yeah.
A question going back to disorder.
Yeah.
This very nice correspondence that you just showed between band structure calculation of basically the maximal density of states and your phase diagram is very compelling. But I mean, shouldn't disorder have played a role in kind of slightly shifting things, or maybe that is there? The agreement is only qualitative, not actually quantitative, right?
The argument is actually qualitative. So in fact, if you investigate for a few moments, so for example, we see that there is, I mean, it's a little bit digital, our data sampling. So we don't have like continuum of data, but in the devices we've measured, we see that the maximum Mott gap appears for 5 degrees, for example.
Mm-hmm.
And the density of states argument would suggest that that should be closer to 4 degrees. So there's kind of quantitative differences between this kind of model and our data.
Mm-hmm.
But, as you appreciate there's certain assumptions that go into the model that even before invoking disorder that make these quantitative correspondences a little bit tricky to, nail down. It's also the case that, so our collaborators attempted to make some effort to identify if they could actually predict quantifiably how the Mott gap might evolve as a function of twist angle, but that's like a little bit fraught. So I'm not going to show that because I think it's.
All right, I get it, thanks.
Yeah, excellent.
This is Mohammed. I had a question.
Go ahead.
Most of this data was for the valence band, correct?
It's all for the valence band, yes.
And then was there a reason that you didn't go to the conduction band, and also the effective spin orbit? We know that the spin orbit is weaker in the conduction band.
Yeah, exactly. So those two things are both considerations. So that definitely is one thought that, if you could probe the conduction band, there would be substantial differences probably because the spin orbit is weaker and you might have overlap with this kind of other spin band. The technical reason why we didn't go to the conduction band is that we can't physically dope the carriers to the conduction band and do transport measurement.
Yeah.
So this is a consequence of how we physically make contact, the metal we use to make contact, and the intrinsic doping that seems to generally be present in these materials. So it's not a truly intrinsic semiconductor. The chemical potential, as we get it from the furnace, appears to be near the valence band rather than near the conduction band, which allows us to push in the conduction band more than the valence band. Sorry, the other way around. It allows us to push in the valence band.
No, I got it. Yeah, okay.
Yeah.
And maybe okay, we can chat about it.
Go ahead, yeah.
Optically, you can create, maybe optically you can actually dope it to the.
Yes, absolutely. So there's a lot of work that we're doing here. Others like Phi, I'll touch on a little bit, Phi at Cornell and Feng at Berkeley are looking at like similar physics in the conduction band by optical spectroscopy. We also are thinking about whether we can actually just, charge pump to the conduction band and understand whether similar physics is there or not.
And it's actually very intriguing because then you don't have normal excitons. You have these Mott excitons.
Exactly. Yeah, that's right. So, yeah, that's right. Yeah.
Okay.
Okay, great. And those excitons live in a spatial potential. So there's all kinds of cool things that could happen. Yeah. Okay, so here I'm just going to touch on, this is data that I don't think we've published. Maybe it was in the supplemental of our previous paper, mostly because we don't fully understand it. So I'm just going to tune the knobs and tell you what we see. So here we're looking at a specific device as a function of applying a magnetic field more carefully in terms of how the Mott gap evolves as a function of magnetic field. And so qualitatively, what I'm going to describe, we see across some number of devices, but again, we don't have a lot of data yet or a full understanding. But the short story is that as we apply an out-of-plane magnetic field, so first of all, we apply an in-plane magnetic field, we see that the system doesn't respond at all to in-plane magnetic field. But that actually is not surprising. It's known for a long time that The picture I showed you of the spin value locking, where I have spin up and spin down states in the K and K prime points. It's also the case that the physical direction of the spin is more or less fixed. So there's a large energy barrier one has to overcome to cant those spins away from being out of plane. And so as we apply an in-plane field, it's not just that we would see an effect of varying Zeeman terms specifically. It's more that this sort of out-of-plane spin locking would have to be overcome before we see any dependence of the parallel field. And the size of the parallel field that's required to reach that regime is just way larger than we can do experimentally right now. So that's just to say we apply an out-of-plane magnetic field, try to see if we see any evidence of whether this Mott gap is spin ordered or not spin ordered, et cetera. And we see no effect, but that doesn't say anything one way or the other, is the argument I'm making. But what we can do is apply an out-of-plane magnetic field and measure, for example, the evolution of the Mott gap as a function of out-of-plane magnetic field. And what I'm showing in the top right here is how that resistive feature evolves as a function of field for different values of the displacement field. So when the resistive feature is largest at 0B, that's for a displacement field value where the Mott gap is most robust. Again, this is at fixed angle. Then as we apply an out-of-plane field, we see that, that resistive peak just linearly decreases towards 0 with increasing magnetic field. And the shape of that decrease is like a little bit complicated as we vary the displacement field. So when we're in a displacement field regime where the gap is even like effectively non-existent, we see a non-monotonic response that's shown here. So at 0 magnetic field, there's no resistive peak. We apply a magnetic field, we see a resistive peak, and then that peak goes away. Whereas when the resistive peak is strong, it just monotonically decreases to 0. And so here we can plot the actual evolution of the gap as a function of out-of-plane field. And what we see is that the gap is nominally unchanged up to a point. So it seems like the gap is more or less constant. And then beyond some threshold parallel field, it starts to decrease, and it seems to decrease linearly as a function of increasing B. So without making an interpretation of why this is, this looks like potentially there's some B field induced transition in the order of the ground state. So for example, there's some ground state order that's insensitive to B, and then beyond some threshold magnetic field, we see a linearly decreasing with B. And whenever you see a linearly decreasing with B, the first thought is that this looks something like a Zeeman energy, because Zeeman goes linear in B. And if we just assume that, we can fit a line to this and extract the Zeeman coefficient, which would be the G factor. And if we do that, then we plot the G factor as a function of D. What we see is that the G factor shows either a kind of unchanging or weakly non-monotonic response. But notably, what we find is that the G factor is maximally at the same displacement field value where the gap is maximal. And it's enhanced relative to the bare G factor. Okay, so this, if one had to make an interpretation ignoring how Coulomb energy evolves as a function of parallel field, this might suggest that this is a spin unpolarized ground state with a G factor that is determined by, that is enhanced due to interactions being enhanced in the system as the Van Hoff singularity sort of moves to the halfway point. Okay, so again, that's sort of pure conjecture at this point. So anybody who has thoughts about that, I'm happy to hear afterwards.
Cory, when you say spin unpolarized, that actually includes antiferromagnetic ground state also.
Yes, yeah.
Correct? I mean, right, it's not a ferromagnet. That's the approximate conclusion based on that linear falling off. Okay, I just
yeah. So I think, I forget if I'm going to talk about this later. So the reason why that might be interesting is, I didn't emphasize this, I apologize. The symmetry of the Moire superlattice in this system is triangular. At least we think that's the case. And so if we have an antiferromagnetic ground state on a triangular lattice, then that can be an interesting scenario, because it could suggest that we have kind of either some kind of frustrated magnetism, or we have this 120-degree state where the spins are all antiferromagnetics aligned. Yeah. The pseudo-spin is aligned in plane in some way, et cetera.
Yeah, that's the one I'm thinking. But yeah, you're right. There could be a quantum frustration. There could be frustration also, yeah, because of triangular, yeah.
Yeah, and also just sort of a detail, but as I pointed out, there isn't really true spin order in the system. It's sort of combined spin and value order. And so there are interesting ways in which that can be stabilized. Some kind of ordered state in that spin value disorder, spin value pseudospin can be realized. Okay. Okay, so last question about the system is, Does it superconduct? So we have a flat band, we have a correlated insulator and half filling. In twisted bilayer graphene, when we realize those two scenarios and we dope away from the correlated insulator, we see a very robustly a superconducting state. And so we explored the same question here. And what I want to say is that there's some suggestive result, but it's not definitive. And I'll explain that sort of in a moment. But broadly, what we see is that if we look at the temperature and carefully look at the temperature density dependence around this half filling insulator, this is for the device at 5.1 degrees twist. Then at some point, proximal to that insulator, we do see a pocket of resistance that looks like it's zero valued. And if I look at the rho versus temperature dependence, then we see that basically metallic behavior with a more rapid decrease towards zero as we lower the temperature. So in some sense, this resembles what you might expect to see if there were a superconducting transition. But I just want to be cautious about this declaration because zero valued resistance is not on its own definitive proof of superconductivity. This is a disordered mesoscopic scale system. There are reasons why we might see a drop in resistance measured in a 4-terminal transport measurement that are just due to disorder. It's also possible that there's basically a Fermi surface restructuring that happens when the Mott gap forms, and that can give rise to a shift in the resistivity that you measure, and that resistivity may become low, but whether it's truly zero or not, and whether it's truly superconducting or not, is sort of difficult to say. One of the challenges of the 2D superconductors is that, historically, if you wanted to claim you had a new superconductor in a 3D material, you would show two metrics. You would show that the resistance goes to zero, obviously, and you would also show perfect diamagnetism, would be the other kind of half of that check mark, that box you'd want to check to say, yes, it definitely is superconducting. In 2D materials, you don't have perfect diamagnetism. One way to think about that is that the Pearl length can be basically infinite in size. And so you can get penetration of the field through the 2D superconductor, even in the superconducting state, even at zero, very close to zero magnetic field, et cetera. So the community at large has developed some metrics to try to identify whether you have a superconductor or not in the 2D limit. One is you can look at the IV response, so that's not really definitive. The most definitive measurement that's been reported repeatedly for twisted bilayer graphene is that if you look at the field density dependence, you see something that looks like a Fraunhofer pattern that emerges, and that Fraunhofer pattern is pretty clear signature that you probably have a superconductor. So we do not see Fraunhofer in this system. That doesn't mean it's not a superconductor. It just means that we don't have sort of infinite confidence that it is. Okay. One thing I'll note is that where we do observe the zero resistance pocket, which may or may not be a superconducting state, we see that in this device and another one I'm not showing data from, which is at angles near 5 degrees, more so than at smaller twist angles. And what I noted before is that around 5 degrees is where we see the maximal magnitude of the Mott gap. So that seems suggestive because it suggests that where we see a state that might be a superconductor, it seems to be stabilized when the Mott gap is also strongest. So that would be consistent in a hand-waving way with possibly the scenario where the zero resistance state is stabilized where the band, where the correlations matter the most. So if I take the strength of the Mott gap as a proxy for how strongly interacting the electrons are in the system, then we see the zero resistance pocket where the Mott gap is strongest, et cetera. Okay. One more thing. So these are kind of new mysteries. We started to look more in detail back at these devices away from the half-filled insulator. Here I'm looking at a 4.8 degree twisted device. This red strip in the middle is presumably the Mott gap. This is at half filling. And what we see are there are a number of features at lower doping that look like local resistant features also. So if I look at these in detail in a crosscut, this is different temperature values. Blue is cold and black is warm as a function of normalized filling. Then indeed, I see that in addition to this half filling peak, there are repeatedly sort of oscillations in the resistance value. And based on our understanding of where the half filling point is and where the zero filling point is, we can just put down labels of fractionally filled values. And what we see is that these oscillations seem to be coincident with well-defined fractional fillings. So this would be consistent with a picture where in the system, what we're actually seeing is evidence of Wigner crystal formation or charge density wave state formation at rational fillings of the superlattice potential. So one example of how that might happen, I just took an example from a talk I gave about Wigner crystal charge density wave formation in pattern graphene in the quantum Hall regime. But anyways, the idea is that I imagine that I have my electrons, I'm putting them into a system, and here in orange, what I'm showing is, for example, a superlattice potential sites that might exist in the system. And for certain rational fillings, you can realize scenarios where the electrons kind of condense onto these lattice sites. So that's what we might call a charge density wave state. And here I'm showing like kind of an unusual or unexpected scenario where they condense in such a way that effectively you get stripe phases, but it's still a commensurate filling to the underlying lattice. So this would be something like a filling that has 2 times the area, or like, a quarter filling of the overall filling of the lattice. Okay, so there's been several reports of phenomena like this in heterobilayer TMDs. This is work mostly coming from the groups of Feng at Berkeley and Mac at Feng Wang, sorry, Berkeley and Phi Mac at Cornell, where by optical spectroscopy mostly, but also some transport data, they've identified that actually in these Moire patterned TMDs, you can get a whole like plethora of insulating states emerging at fractional filling, which are variants of this Wigner crystal type phase. Okay. One more thing about this system is we looked in detail at the temperature dependence above the temperature value where we have these correlated states. And we see, again, some similarities, but also some differences to what we saw in twisted bilayer graphene. So just to recap, in twisted bilayer graphene, our group and also Pablo's group previously published some work showing that actually the resistance as a function of temperature evolves linearly in this band over certain density ranges and certain temperature ranges. But not only is it linear, the coefficient of linear dependence is very enhanced compared to what you see in kind of native graphene. So we had considered a picture of some kind of enhancement of the phonon coupling in the system that might explain this enhancement of the linear T behavior. The MIT group promoted a view that this might be evidence of strange metal, which you might expect by just sort of like pattern matching in terms of twisted bilayer graphene hosting Mott and superconducting states and comparing that to what is seen, or at least thought to be understood in some of the high TC superconductors. So this, in a sense, is a kind of open debate within the community of like what this linear in T response actually means and when it actually is precisely linear in T and what the coefficient means, et cetera. So I won't get into that debate. I just sort of highlight that this conversation began with twisted bilayer graphene. So we started to look at this again in twisted bilayer WSE2. What we see is that the temperature dependence above the temperature at which we have the Mott gap is pretty interesting. So here I've got a same 4.2 degree device, same device I've been discussing for most of this talk. And what we are looking at here is sort of line cuts and temperatures. So I go to a fixed filling. Sorry, this is normalized filling. So right around here is half filling. So I go to a fixed filling and look at the temperature dependence of the resistivity. And what I see is that over a range of fillings, it looks like in the low temperature limit, this response is very well fit by T-squared dependence. Here, it's sort of very overdoped and very underdoped. And near optimal doped, where optimal doped is where the Mott gap half filling, where the Mott gap exists, the temperature dependence appears to be more like really robustly linear in T. So we can map this out kind of broadly. So here's a cartoon map of what I mean. So here's temperature on this axis and filling. The brown regions here are basically, this is the half band insulator and this is the full band filling point. And what we see is that adjacent to the half band filling, there seems to be wedge-like features which show a T linear dependence, and then doping beyond that seems to show a T-squared dependence. So if this is the Mott gap, then we are discussing right now internally and with Sankar in the past week, whether this is possibly evidence of a quantum critical point in the system.
Cory, I have a factual question. Where in this picture be this putative or suggestive superconducting phase? That seems to be gone now, right?
Yeah, so we didn't see that in this angle device. So as I mentioned, we saw that kind of robustly in the 5 degree device, but we haven't actually identified it in the 4.2 degree device.
So when the angle changes, it's actually a new device, right? There is no
Yes.
the same device, right? It's a different device. Okay.
Yeah, so you raise an interesting point. I hadn't thought about this, which is to look at the T dependence
Yeah, I mean,
around the 5-degree device. Yeah.
Right. You should definitely do that. I just assume it's the same device, but it isn't. Yeah. Okay. All right. I mean, that can be done, right? You still have the device, right?
Hopefully, maybe not. But, yeah,
Okay.
yeah, but we can make new ones. So yeah. Okay, so this is new data that we don't, this is maybe a few weeks old. So I don't really understand this a lot. I just want to show it to kind of motivate some discussion or thought if anyone listening wants to discuss this further. Okay, so I'm kind of out of time. I'm gonna just very briefly, if you'll permit me, sort of extend this discussion a little bit beyond twisted bilayer MOS2. Can I take like 5 minutes? Is everybody okay with that? Or does anybody object to that?
Yeah, we had questions, so please go ahead. Yeah.
Okay, yeah. So what I want to do, so as I said, I've been talking exclusively up until this point about twisted homobilayer, and we were looking at WSC2. But as I mentioned before, there's a wide range of transition metal dichalcogenides that one can consider. And one thing you might think about is making twisted homobilayers of the different flavors. But the slightly more interesting thing is to make twisted heterobilayers. So that's introducing one transition metal dichalcogenide onto another one. And in this case, these are naturally lattice mismatch generally. So whether you twist or don't twist is not super relevant. In all cases, you'll end up with a typically a moire superlattice. But also what happens in this system, because the work functions are different in these materials, is that you typically get a different scenario. So we understand these systems not so much by the fact that the layers kind of hybridize between each other. It's more that the energy bands are displaced relative to one another. So here's a cartoon example. This is taken from a paper by Phi Mac at Cornell. They were studying WSC2 on WS2. And what they argued is that basically, so the cartoon picture here is showing, suggesting that the low energy band is actually gapped. So this would be the Mott gap, for example, in their cartoon picture. And the chemical potential in the system is living entirely in the WSC2 layer, and the WS2 layer is in the gap because the top of the WS2 valence band is much lower in energy. So in a sense, this is even a simpler system of what I've been discussing. Now we are thinking about a situation where we have basically a monolayer WSC2 that sees a superlattice potential because it's in proximity to the WS2, but the WS2 bands are more or less not relevant. So that's interesting because this gives really a simple kind of access they promoted, Phi promoted, to an experimental realization of a triangular Hubbard model. And what's cool about this sort of opportunity is that the parameters of this Hubbard model are very tunable. So the site-to-site distance is tunable by basically correlates to how big the moire superlattice is. So if I take two different materials with different lattice mismatching, I can expand or contract the moire wavelength. Or if I take a single heterobilayer and twist it, that's another way that I can dynamically, vary the wavelength of the superlattice potential, which directly varies the hopping term in the Hubbard model, for example. The other is that as I introduce different layers with respect to each other, the magnitude of the superlattice potential can be varied. It turns out quite dramatically, and so on. So I just want to put this picture up to sort of advertise that this is really a rather robust platform and sort of like a rich platform in which to study a lot of kind of variants of this sort of idea of, Hubbard model. So here's just a short list of like combining different currently accessible, reasonably high mobility 2D materials that we have access to in our lab, 2D transition metal dichalcogenides. And all I'm showing here is basically the lattice mismatch. So 4% lattice mismatch for most combinations. For these two, it's a much smaller lattice mismatch. So what has been studied almost exclusively by others to date is this system here, WSC2, WS2. For reasons I'm not exactly sure. So we decided to look at this system here where the lattice mismatch is much smaller. And what that gives us is access to a situation where the moire period is much bigger than might be accessible in other systems. Okay, so just very briefly, I'll just take a minute, I'll skim through this very quickly. Here's some SCM imaging not done by me, but by Abai Pasapathi's group, also at Cornell, in which they show topographic images basically of WSC2, WSC2 MOSC2. Is this right? What am I looking at here? WSC2 MOSC2, that's right. And the thing to note here is that if they're in 0 degree orientation or 180 degree orientation, the symmetry of the superlattice potential is radically different. The other is that they measure the magnitude of the superlattice potential, and it's remarkably large. So they measure spectroscopically the Moiré potential to vary by about 35 MeV, 350 MeV from peak to valley across this landscape. So that's like an enormous potential to be able to apply just by this effective potential, just by this kind of superlattice patterning. So we looked at the system in transport, so same system, WSE2, MOSE2 bilayer. We realized a device in which we can measure both transport and capacitance measurements. So I'll just cut to the chase. Here's the effective result here. So what we see is that in transport measurement, we see that basically it's in transport anyways, going to Sankar's question from before, it's hard to sort of, measure any transport response through most of the low energy band that exists until we're sort of almost doped near the top of the band. But if we look at capacitance, we can see very clearly, here's the intrinsic band edge of WSE2. Then we see a peak in compressibility, which is signature of the insulating state at the half filling point. And then we see a little sort of variation as we exit that low energy band and move to the high energy dispersing bands. We can look at the temperature dependence of this material. What we see is that as we cool it down, there's a lot of sort of nuanced responses. I think I'm not going to go through this because I'm a little bit running out of time, but the basic idea is that we see very clearly the band edge associated with the low energy band when we measure by capacitance. We see very clearly an insulating state that emerges at half filling. And we also see very clearly signatures of insulating states at partial filling, so 1/3 and 2/3 filling in this case. We also see that in this particular sample, at the lowest temperatures we can measure, the entire low energy band becomes totally insulating at all filling fractions. So that we think is related to the fact that the Moiré potential is so large. And we think that basically at low temperature, we're kind of condensing the electrons, or we're localizing electrons on the superlattice potential itself. So another way to characterize that is we are imagining that the superlattice potential is basically acting like an insulating lattice in the system. The other thing we see is that the transition temperature over which the electrons localize onto this superlattice potential is different if we're below half filling versus above half filling. So we think that might indicate that this isn't just a pure kind of single particle effect of electrons, being trapped by the superlattice potential, but there may be some many body effect that's helped mediating that. Okay, then finally, magnetic field dependence shows that there's a difference again between below half filling and above half filling. So below half filling, if I'm in sort of one branch of this gapped flat band, then in this case, I see that as I apply magnetic field, there's basically no effect. Whereas if I'm in the other half of the band, at some well-defined magnetic field, I see a transition from an insulating state to a conducting state. So one way to understand this is pure conjecture, is that in this case, if the gap associated with half filling would characterize like a ferromagnetic ground state, then I might imagine that for below half filling, so if this branch basically is ferromagnetic, then I wouldn't expect to see a B field dependence. But if when I dope into this point, I have something more like a antiferromagnetic response or antiferromagnetic ordering, then I might see a sort of, a transition out of that insulating state as I apply a magnetic field. Okay, so that's, one thought that I'm not going to marry myself to, but just sort of, initial interpretation of the data. Okay, so the other thing we see is that there is some hysteretic behavior. And we see that, so this is only present as far as we can tell if we're doped from about the middle of this band up to about this point. And what we see is that this hysteresis and transport, as we vary the magnetic field up and down, is symmetric around a finite field value. It's not symmetric around a zero field value. And this might be, again, consistent with some kind of antiferromagnetic ordering. But interpreting resistive response in terms of magnetic ordering is a little bit difficult. So that's, again, sort of a conjecture at this point. Okay, so I'm going to finish there. I just want to summarize that there's many twisted systems that we can look at. Twisted bilayer graphene has received enormous experimental sort of, investigation interest, and we already understand a lot about that system. There's much more to understand to go. Twisted bilayer TMDs, or homo TMDs that are twisted, or heterobilayers that are not twisted, also provide a lot of interesting sort of new opportunities in terms of the kinds of states these systems can host. And overall, we have just a remarkable opportunity for understanding tunable band structure, magnetism, superconductivity, topology, et cetera. I'm not gonna talk about these slides. I'm gonna point out that I did prepare a few slides about disorder that I thought Sankar might be interested in, so we can come back to that if we want at the end. And I'll finish there and sort of thank the many people who have worked on this over the past few years. Thanks for your time. I'm happy to answer questions. Yeah.
Thank you, Cory.
Thanks. Yeah.
Okay, now it's open to questions. Please just go ahead.
Cory, this is Jay.
Yes.
Okay, yeah, so Jay, so quick question. So I guess this is gonna sound very similar to what Shankar asked at this Wigner conference like last week. So when you say Mott insulator at half filling, is it really basically an insulator at half filling that shows some signs of correlation? Is that the definition, or is it more specific in the related to the Van Hove singularity? That's the one.
Yeah. So I think that's a great question. So I think when we started to study the system like a year ago or so, when we saw an insulating state, one question you might ask is that insulator coincident with the Van Hove singularity, or is it really coincident with half filling of the band? And my understanding would be that if we could definitively show that the insulator is at half filling always, even if the Van Hove singularity moves away from half filling, that would be consistent with it being a Mott gap, because the insulator emerges when we have one hole per Mori unit cell specifically. Then you ask the question, suppose I'm at one hole per Mori unit cell, under what condition would I or would I not get an insulating state? Would there or would there not be a Mott gap? And that relates to the energetics of the system, right? So let me try to cast this in a different way. So let me have this low energy flat band, fill it so that I have one hole per Mori unit cell, and ask, is the system going to form a Mott gap? Whether it forms a Mott gap or not depends on how strongly interacting the electrons are, in a sense, right? And our argument is that in this system, we actually can tune that variable about strength of interactions, because we can move the Van Hove singularity point close and far away from the half filling point. Or another way to think about that is we can move, we can vary the density of states at half filling in a funny dynamic way. So let me address that one different way. We think we can move the Van Hove singularity away from half filling. And what we do not see is that when we move the Van Hove, the gap shifts with the Van Hove. The gap stays at half filling, even if we shift the Van Hove away. So one answer to your question I can say is that we're very confident that the gap is not coincident. It's not determined, the gap doesn't follow in filling where the Van Hove does, right? The gap is always at half filling. So because the gap is always at half filling, because it seems to form over a narrow range of temperature, it's a half filling, it emerges in a scenario where we think the correlations are strong. For those reasons, we characterize it as a Mott gap.
Yeah, maybe
excellent.
Maybe I'll quickly comment on it also. Heining's mean field calculations are showing, again, I do not like using this mod and this terminology, but it's showing that what Cory is saying is what happens. Unfortunately, we call that nu is equal to 1 because we count filling as how many holes per unit cell. So what Cory is saying, half filling, we call nu is equal to 1, which is 1 hole per unit cell. So that's half filling. We find that there is always, quote unquote, a Mott gap, meaning, of course, our calculations are a Mott calculation. Our calculation keeps like, I think, 2,000 next nearest neighbor interactions, not just on site. So this is not Mott Hubbard, okay? But we find in general what we call antiferromagnet. It's not a strict antiferromagnet. It's a triangular lattice, hexagonal lattice. Spins are not aligned. Spins are rotating in some manner. So that, I think, is consistent with what Cory is finding. Again, this is a mean field calculation, which is all what we can do. But the calculation is realistic. Calculation is realistic, meaning we fit it to their measured band structure from STM, parameters of the mean field band calculation.
I see. So just to but strongly interacting is defined by Van Hove singularity being near half filling, but what you're saying is that the filling of the insulator does not track the Van Hove singularity when it moves away.
Exactly right. Yeah. Right. So there's another kind of nuance there. So I want to be a little bit careful. The language of strong interactions, probably one should define. So the degree to which we're in a strongly interacting regime is unclear. And in fact, we're probably more like in what we call a moderately interacting regime. Because we're actually operating at a pretty high twist angle. It means that we're operating in a regime where it's probably not the case that Coulomb energy greatly exceeds the bandwidth or even exceeds it at all. They're kind of comparable, we would expect. And that just happens to be the case in terms of like what angle range we can experimentally access. But because of that, I think that's why we see this effect of shifting the Van Hove, because we're kind of in this like moderately interacting regime, and we can kind of put the system over the edge by tuning the Van Hove to have to kind of half filling, if that makes sense. Yeah.
Yeah, absolutely. Thanks.
Can I ask something that might be related? I'm not sure. I noticed in quite a lot of the plots of the half filling peak as a function of density that there was a pronounced asymmetry in the peak, and I was wondering if that indicated something interesting about the interactions, or if that was just inherited from the underlying band structure, or was an experimental detail, or what that might have meant.
Is my screen still sharing? Or are you
yes.
still, yeah. So
yes.
Do you mean, I didn't get what you mean. Do you mean like this plot, for example?
Yes, exactly. Yeah. I mean, there were some more pronounced examples in your earlier slides, but yeah, that shows the kind of thing I mean.
So you're asking about the asymmetry in the resistance value as a function of density?
Yes, asymmetry about exact half filling. Yeah.
I don't know how robust that is. So that could be interesting, and it could also relate to some experimental details. So for example, we do know pretty well from studies of just monolayer WSE2 that disorder in the band kind of varies pretty strongly as you measure disorder, as you move from the band edge into the system. Mobility kind of varies rather strongly. So if you're just using resistivity as a proxy, I'd be a little bit careful, because it is the case that there would be an asymmetry around half filling in terms of mobility of the carriers. So I'm not exactly sure. I'd be a little bit careful with that. But there are, if this is a system in which we have a frustrated, triangular magnet, there are certainly conjectures that as you dope outside of the Mott gap, you might get, some kind of exotic spin state, for example, and it's possible that that couples to our resistivity data. So, I don't want to reject the kind of most interesting sort of possibility, but I'm not so sure at this moment. Yeah.
Okay, thanks.
Is there any other question? Okay, I don't see anyone. So if not, let's thank Cory again. Thank you for your very nice talk.
Yeah, thanks everybody for listening. I appreciate the opportunity.
Cory, I actually had a question.
Okay, yeah, Muhammad, please.
For these Motts, you said that people are looking at this optical response of these systems. But our understanding, we have been actually looking at Mott excitons, but for cuprates, not for this Pylar system. So it was actually very intriguing to see that these kind of Mott states develop over here. And then you have a very strong binding energies for these TMDs. And do you know whether people have actually looked into see the creation of these Mott excitons that are very different than the usual excitons in TMDs?
I know people are actually looking into this. I don't know what the current sort of understanding is in terms of what is possible. So one of our collaborators at Columbia, this guy, XYZ, we call him Xiaoyang Zhu. So he's been looking at basically, if you take these heterobilayers and you blast them with a really high intensity kind of light, what happens? So he thinks he's identified, I don't remember if this is published, but he thinks he's identified that basically you can create these Mori excitons, and then you can go to the point where you kind of break the exciton pair because they have so much energy, and you sort of go through this plasma transition, and then you have these kind of free carriers. So whether he's actually looked at that physics when there is a Mott gap present or not, I'm not exactly sure. I'll ask him about that. I don't know the answer to that.
The reason is that it not only be binding through the Coulomb interaction, but through some spin mediation interaction. Because you have the Mott, and you just start with a simple Hubbard model, and then you can actually see that you can get binding. So it would be an interplay between just the normal Coulomb binding and then this is spin-mediated bonding.
So to be clear, the Mott exciton, sorry, maybe I misunderstood. This would be the electron hole pair includes a pairing with the other conduction band?
Yeah, let's say, for example, you're in the valence band, and then I have a holon and a doublon. And these two can bind in the absence of the usual. So forget about the conduction band. You're in the
exactly right.
Band.
Yeah.
And then I have a holon and a doublon, and these two can actually bind. So I'm like a spin-mediated situation, and that forms a Mott exciton. That's one
cool.
form.
Yeah.
That's one form of one exciton. There is another form of one exciton that people have linked to. So then the energy of this binding is of course much smaller than the usual binding energy of an exciton, which is almost equal to the size of the gap. It's like a fraction of a gap. So if one does you look at the exciton line, like it's the first S exciton line, and then see that it shifts by the amount of this Mott binding, then that might be also another indication of the creation of these Mott excitons. Apart from this band structure calculation and then showing this might be actually you should. I'm just thinking now online.
Yeah, no, I think it's a really good idea. So I'm not sure. I don't know the answer to whether this has been either looked into or identified. One challenge I imagine would be a little bit of a concern is that the gaps that we measure are small. So the Mott gap is like few MeV or something, right? It's quite small. So pumping light into the system to do that kind of spectroscopy might already sort of heat the system too much to sort of see this kind of physics.
No, so it's between a weak excitation. So it and the exciton.
Oh yeah, you're right. Yeah.
Two MeVs anyway. So we are now in the same order. So if it's if you're saying that it's MeV, then it would be just a few MeV shift of a line that is also MeV thick.
Oh yeah, that's interesting. Okay, okay. So another thought I'm just going to promote because it's something we're trying to do experimentally now is that the way I think about this flat band with a Mott gap is that we know this experimentally that the Hall sign inflects around that Mott gap, which you would expect because it's a gap. So there's some question about how far in density you can extend and still have your band modified by the presence of the Mott gap. But ignoring that for a moment, then what that means is that actually I can tune from electron light carrier to whole light carrier with a very small electric field, incredibly small, right? And what that makes me sort of interested in is revisiting these notions of making like interlayer excitons, but now using this as a platform. So now imagine that I have, flat band WSE2, forget about how you realize it. And I have another flat band WSE2 system and I spatially locate those close together. Then it's actually now becomes practically possible that in one system, I can have electron carriers and the whole carriers on either side of that Mott gap, with just very small sort of, fields applied, which means the interlayer fields are also very small. And those systems are flat, which means they're already strongly interacting. So in my imagination, this is sort of a nice way to revisit the question of like how to make exciton condensates, because now this is a scenario where you can do this with two materials that are already very strongly interacting flat bands and solve the problem of like, how do I get one to be nominally electron-like and one to be nominally hole-like within reasonably applied fields? So I don't know if you hadn't thought about this previously, maybe we can talk separately. Maybe it's sort of too much.
Yeah. I'm actually teaching in 2 minutes, so I should probably log off. But I would love to continue chatting with you. Yeah, in particular, I know what you're saying. You're saying that I flatten the band, so then effectively also for this exciton interaction that people have been trying so hard to increase it, and then it just comes out for free.
That's right. Yeah, I think so. Yeah.
Okay. Good to see you.
Okay, thanks. Yeah, thanks.
Okay, I think that's all for today. Thanks, Cory. And let me start recording. Stop. Okay.